You're listening to the Land Use Podcast, brought to you by the Alberta Land Institute.
Geothermal provides us the base load. It's not an intermittent source of energy like wind or solar power. We can provide people in remote areas in Canada, like First Nation people, with green, sustainable energy for free. Maybe even one well can heat more than one house. This energy, we need to pay more attention to it because it's technically available everywhere.
Hello and welcome back to the Land Use Podcast. I'm Aisha Wu, and today we're joined by PhD student Mohammad Zolfagharroshan from McGill University to talk about the geothermal energy potential of abandoned oil and gas wells in Alberta. Before we start, I would like to respectfully acknowledge that the University of Alberta is located on Treaty 6 territory and respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. Across Canada, there are 400,000 abandoned oil and gas wells, with over 172,000 of those in Alberta. Other than frustrating landowners, these abandoned wells can have negative effects on the environment around them. However, the wells may also present an opportunity for heat and electrical generation. PhD student Mohammad Zolfagharroshan is part of a research team that assessed the geothermal potential of oil and gas wells in Alberta. Welcome, Mohammad. Can you introduce yourself?
Sure. My name is Mohammad Zolfagharroshan. I'm a PhD student at McGill University. I'm doing my PhD in mining engineering, and my research topic is geothermal energy from conventional and unconventional resources. One of these unconventional resources is abandoned oil and gas wells. Moreover, I have a background in petroleum engineering, and I'm a member of Mine Multiphysics Lab under supervision of Professor Sosmito, who is the principal investor of this group.
So, as mentioned before, abandoned oil and gas wells are obviously a huge issue in Alberta and across Canada. Could you clarify what an abandoned oil well is?
Yeah, you're right. There are around 500,000 abandoned oil and gas wells in Alberta. And measurements of methane leakage from these wells has shown that they are serious and uncertain source of leakage of methane to the atmosphere. So first of all, to define an abandoned oil and gas wells, a National Petroleum Council of the United States classifies abandoned oil and gas wells into one of these groups. The first group is the wells with no recent production. They call it also inactive wells or temporarily abandoned wells. The second group is wells with no recent operator. They also call it orphaned wells. And wells that are plugged to limit the emissions and fluid migration to the surface. Technically, we shut in hydrocarbon wells that has no financial viability. The most common reason is when a hydrocarbon well is close to the end of its lifespan, or it doesn't produce at a profitable rate, and we call it a mature well. Maybe even a newly drilled well also be abandoned because we might have a dry well. We drill to produce hydrocarbon, but when we reach at the target point, we see that there is no hydrocarbon. It's possible. We may not use that well as well. Another reason can be we drilled a well to inject water for water flooding and producing more oil and gas, and when we did our mission, we are not using that well anymore. So abandoned oil and gas wells can have different definitions. But here we mainly focus on the wells that are mature and they're closed, and maybe they're plugged or unplugged. We are working on the idea of reusing them for geothermal energy.
Okay, and why are abandoned oil and gas wells an issue?
Sure. I mentioned methane emission as a serious threat by abandoned oil and gas wells. Actually, we always highlight the global warming effect of methane emission, but there are a couple of more reasons and threats that methane itself impose. For example, methane can contaminate groundwater and degrade water quality. Another reason is that the pressure buildup by methane has caused explosions in the past. There are records from 1970s to 2007, mainly in the United States, if I'm not mistaken, that explosions led to injuries and deaths in some areas with, for example, there was a mining activity close to an abandoned oil and gas field. there was methane trapped there, and by triggering it led to an explosion. Or even another case was a house that was built on abandoned oil and gas wells, and an explosion happened there as well. And finally, living close to such abandoned wells with uncontrolled methane emission rate also affects human health. It was shown in the literature that there was a correlation between proximity to living close to abandoned wells and the respiratory problems, migraine headaches, or fatigue symptoms. This is just the treat by methane, but we can have also the risk of hydrocarbon migration to the fresh groundwaters, because the well itself can be as a conductor of any fluid, even hydrogen sulfide, H2S, which is a toxic component. By breathing, it can lead to death. These are among the threats that abandoned oil and gas wells, that whether plugged or unplugged, might impose.
Okay, so I can see why it's important that we do something about the wells. And from what I understand, I think remediating them is quite expensive. What motivated you to look into the geothermal potential?
Actually, the project that I'm involved in, it's a funded project by NSERC, and multiple teams at McGill University and also University of Calgary are involved in this project. We are considering different aspects. My co-supervisor, Professor Kang from Civil Engineering Department at McGill University, started by assessing the methane emission from abandoned oil and gas wells. And they noted that we might have multiple options. One of them is reusing abandoned oil and gas wells as geothermal wells. And then she contacted my supervisor, Professor Sasmito, who is expert in geothermal energy. And we came up with the plugging option and also reusing as abandoned wells. The costs can be close together, even maybe retrofitting costs a bit more, but there is financial revenue out of it. If we plug a well, we have a rough estimation that in onshore wells, it costs something around 50,000 United States dollars to 150 USD for plugging. But as I said, there is no financial revenue out of it. And still measurements show that there is methane emission even from the plugged wells. But if we reuse abandoned oil and gas wells as geothermal wells, we are kind of making money out of it. And we are addressing well integrity issues, which is also controlling methane.
We can also save considerable amount of money since we don't need drilling. Drilling can take 40% to 90% of the budget in a geothermal project. And the drilling cost can be as high as $15 million.
This is the positive aspect of that. And we should note that in Alberta, we have heating demands in cold season. There are also other possibilities for reusing abandoned oil and gas wells, like using them for carbon capture and storage, or like further drilling to explore other minerals, such as lithium. But in our team, we are interested in the geothermal aspect.
Okay, so then how did you go about determining the geothermal potential? Like, what was the research process like?
Well, the main objective is to propose a criteria or find the best location in Alberta that we can retrofit and reuse a well, but we didn't know where to start. So we decided to do a statistical analysis, so assessing a wide range of possibilities, and then seeing what criteria or what steps, or what geothermal gradients or what type of rocks are suitable for site selection. Because the final goal of our project is to show the field demonstration of this concept. So we started by gathering database of abandoned oil and gas wells in Alberta, seeing how are the depth distribution, what rock types and lithology are there. The next thing is we need a multi-physics model, like we should solve a transport phenomena, heat transfer and fluid flow inside the well to quantify the amounts of energy that we can get from the ground. Because just knowing the bottom hole temperature is not enough to see how much energy we can get and whether we can use it for heating or can we use it for electricity generation. So we developed that model as well. The good thing about our model is it's computationally efficient. So we can simulate transient operation of the system over long term, just in few minutes maybe. This is why we decided to do a statistical analysis. So we decided to simulate around 10,000 abundant oil and gas wells in Alberta. Now, I guess it's good to mention what configuration we decided to select, because when you want to retrofit a well, you might have different options. This is more about geothermal energy extraction methods. Like in geothermal energy extraction, we have mainly two approaches. We can select open loop heat extraction and we can select closed loop heat extraction. Open loop briefly means that we inject water through the well, and this water goes into the rock. And we usually at least need two wells in open loop configuration, one for injection and at least another for production. So here, the fluid is in direct contact with rock, and the heat exchange happens by contact of working fluid and rock. And closed loop, on the other hand, is when we install like closed network of pipe into the ground. So there is no direct contact between the working fluid and the rock. Each of these approaches have their own pros and cons. For example, the open loop that I described is better for volcanic regions, and where we have high bottom hole temperatures, because we can extract huge amounts of fluid and energy, and the ground recharges the heat. But on the other hand, it also imposes some challenges. You probably need to install some water treatment units at the surface, because there are some minerals that might be dissolved in the water and you are bringing them to the surface. And mineral scaling and deposition is another issue in the facilities you have. And sometimes we need to do hydraulic fracturing. That is kind of challenging. It's forbidden in some countries. We had it also in the petroleum industry, but like in Europe, it's been years that it's forbidden because it can trigger small earthquakes. And sometimes like the fractures that you need to develop, it's out of control. I mean, and when you inject water, the water can be lost and never get back from the production well. That was too much, but it's not that bad actually.
From heat extraction aspect, the issue is that ground temperature is not high enough to boil water and produce steam. So low pressure of the wells can be an issue.
But the closed loop, on the other hand, you have better control over the circulation. You circulate certain amount of fluid between the surface and the ground. When there is no contact between the working fluid and the ground, there is no mineral scaling issue or no water treatment is required. And it's almost zero emission on the other hand. In general, actually, geothermal is a kind of nearly zero emission technology, which is actually environmental friendly. You're not injecting anything to the rocks. So in this study, we selected closed loop, which is more reliable. It's a more conservative option. And regarding the configuration, we selected the double pipe coaxial heat exchanger. To explain it in simple words, imagine you drill a hole in the ground and you install a pipe. And to fix the pipe, you should squeeze cement in the annular area between the outer surface of pipe and the ground. So now you have a well, you close the bottom side of the well, and then you put another pipe with open end in this well, and you start injecting cold water through the annular area between these two pipes and extract heated working fluid through this central pipe. And this central pipe is thermally insulated. This is the configuration that we decided to select to simulate these 10,000 abundant oil and gas wells.
And what were some of the findings?
Yeah, to explain the findings, first I should mention what operational conditions we assumed. In Alberta, for example, when in winter, the temperature outside is minus 30, even getting 5 degrees, 10 degrees, 15 degrees Celsius can be something to heat, for example, some industrial units. So we decided to consider water circulation rate of 1.66 kilogram per second and inlet water temperature to be 15 degrees Celsius. When we simulated the 10,000 wells, we noted that around 80% of the wells showed positive and promising potential to be used as geothermal wells and deliver geothermal energy to the surface. Actually, when we inject 15 degrees, we even got higher temperature, like up to 100 degree, 150 in some locations. So I should elaborate that among the 80% wells that showed promising potential, around 99% of them were suitable for heating applications, and around 1% showed potential for electricity generation, which kind of makes sense. Actually, Alberta is not on the ring of fire, or there is no volcano there, but still this kind of good results. And actually, in our paper, we explained more details, but here I try to explain the key findings. For example, we decided to classify the wells based on the outlet water temperature that we get. So we inject 15 and we might get anything. So to generate electricity, we need minimum outlet water temperature of 90 degrees Celsius to connect it to an organic Rankine cycle. So this was one of our criteria. So we classified the wells that gives us an outlet water temperature of 90 or above as ORC wells, organic Rankine cycle. And between 15 to 90, we divided it into equal divisions. We called the wells that gives us outlet water temperature between 15 to 40 degrees, low-grade heating wells, the outlet water temperature, if it's between 40 to 65, medium-grade heating wells, and the outlet water temperature between 65 to 90, we called it high-grade heating wells. So like organic Rankine cycle wells gives us pretty high outlet water temperatures, but they are usually deep wells with higher geothermal potentials. I can say that on average, the geothermal gradient should be something around 34 or 35 degrees Celsius per kilometer. And the depth on average is around 5.6 kilometers, which is quite deep. But we could see even at like around 4.4 kilometer, we can see wells with potential for electricity generation. And the downhole temperature that can produce electricity is something around 200 degrees Celsius. And on average, we can get outlet water temperature of 110 degrees Celsius, which is quite good for generating electricity.
These wells can give us over 800 kilowatt of thermal energy. If we convert this amount into electricity, we get something around 80 kilowatt of electricity. But if we decide to use it for heating applications, we can heat up over 200 houses by a single well.
For the high-grade heating, the average depth is around 4.6 kilometers, and like outlet water temperature is something around 74, which is quite good for direct use and direct heating. The medium-grade heating wells are on average at 3.4 kilometers deep, and they can give us an outlet water temperature of something around 48. The thing is, a great majority of the wells are in the low-grade heating group. Around 7,400 wells are in this group. So I divided the results into smaller groups to increase the resolution of the wells that are in this category. The good thing here is that you can even have small temperature increments. When you inject 15, you might have like 16 or 17, which is minor, but whether using it directly or using a heat pump with a coefficient of performance of 3 to 5, you can enhance it and use it for household heating. And for example, if the injection temperature is 15 and the outlet is something around 16.6, the net energy we can get is around 1.88 gigawatt hours over 20 years. If I convert it to power, it's something around 10 kilowatt of thermal energy. So to give you some numbers, like in cold seasons in Canada, for heating demands of a house, we might need something around 1 to 2 kilowatts. And I mean kilowatts of thermal energy, not kilowatt of electricity, which like 10K is much more than that 1 to 2K. So maybe even one well can heat more than one house.
But this was the minimum value for thermal power. The amount of thermal power we get from abundant oil and gas wells in low-grade geothermal wells reaches to 150 kilowatts. This number increases to 250 kilowatts in medium-grade wells, and it reaches 400 kilowatts in high-grade wells, and for ORC group, it's over 800 kilowatts.
Oh, wow, that's quite good. So are you able to kind of speculate how much of an impact using geothermal would have on Alberta's electrical grid?
Actually, electricity part is a challenging part. We haven't started that yet because one of the challenges that electricity generation has from geothermal is connecting it to the national grid. Our estimations show that even the cost of connecting it to the national power grid, might be more expensive than retrofitting the well itself.
Oh, okay. That's interesting. I would think, though, in terms of saving on power, just because of the heating potential, that it would impact the grid in that sense. Is that right?
Yes, exactly. When we are using this, in some ways, we are saving electricity. People know more about conventional heat pumps these days. You install like a network of spiral pipes, shallow or deep, vertical or horizontal, near your house, and you can heat up and also cool your house. The COP, the coefficient of performance, there is around 3 to 5. That means if you consume 1 unit of energy, you can get 3 to 5 units of energy back. But here, we don't have that concept. But when we compare the pumping power to the energy that we extract, it's like you are consuming 1 unit of energy and you get like 50 units of energy. This is the interesting part about reusing abandoned oil and gas wells for heating applications.
So, what would you say are some areas of this topic that need a little bit more research?
Actually, we are also working on some new areas to enhance the energy efficiency. Like the technology that I explained is the most reliable technology so far, like injecting single phase water and extracting it and use it for heating or electricity generation. The next generation of geothermal energy that currently we are working on is using phase change. There are specific tools called two-phase closed thermosiphons or also heat pipes. They are commonly used in electronic device for heating and cooling, for cooling mostly applications. But in geothermal energy, researchers paid more attention to two-phase closed thermosiphons. When you use phase change, you are using like boiling and condensation of a working fluid or a refrigerant inside a closed pipe. And the heat exchange rate can be much higher than when you circulate single phase flow. Maybe you hear more about thermosiphons in the next 5 to 10 years, because currently we are working to solve the challenges that they have. For example, the resistance against heat flow, now it's quite high. And you mentioned what areas need to be more focused. In our study, bottom hole temperature could be a limiting factor. So we didn't simulate really shallow wells, the wells that have depths lower than 500 meters, because if you inject 15 degrees, you may get lower outlet water temperature for sure, and you're actually heating the ground. But if you install a thermosiphon there, thermosiphon work based on temperature difference. So the temperature of the ground solely cannot be a limiting factor. And in that way, if we can use more shallow abandoned oil and gas wells for heating applications, that would be good. And by the way, I have to mention that like geothermal is not only for heating, we have heating and cooling in addition to electricity generation.
Oh, awesome. Okay. You may or may not be able to answer this, but basically, what do we need in order to move forward with converting oil and gas wells? Do we need the support of government, industry? What do you think?
Yeah, for sure. The government and companies can help us to boost this technology and this advancement. Still, we have to compare different scenarios. Like maybe some researchers come up with open loop systems and they say this is more efficient. Now we see that the most reliable way is probably closed loop heat extraction. And plugging and abandonment also should be investigated. Maybe it's more efficient. I read in the literature that the governments can help operators. For example, the operators in oil and gas industry, if they drill a hole and the well is not efficient, it's not good, they quickly convert it and switch to geothermal energy. You know, if such regulations are prepared and giving the operators flexibility, that can be useful in this research.
Okay, great. Well, that's all of my questions. Do you have any concluding thoughts before we wrap things up?
Yeah, for sure. Actually, as a concluding remark, in a world that we are recycling plastic water bottles that cost nearly nothing, abundant oil and gas wells can create opportunities for us. Like an inexpensive oil and gas wells, just the drilling operation can cost $1 million. And this can be much higher. So we have this valuable asset that we can use, and we can boost the decarbonization of the energy sector, and we can provide people in remote areas in Canada, people like First Nation people, with green and sustainable energy for free. Because like in oil and gas wells, the infrastructures is already there. The like access roads, everything were prepared one time. And at the end, I have to highlight that like geothermal provides us the base load. It's not an intermittent source of energy like wind or power. And we have minimal land use. We don't have like farms of turbines or cells of solar power. Most of the infrastructure are down there. So this energy, I guess we need to pay more attention to it because it's technically available everywhere. Wherever you drill a hole and go down, as a general rule, the temperature of the ground increases, and you can use that for free to heat up your house or use green electricity.
Yeah, that's an excellent concluding point. Well, thank you so much, Mohammad, for joining me today.
Thank you so much.
And that is it for this month's episode. If you're interested, you can learn more about Mohammad's research from the link in the description. If you enjoyed the episode, you can leave a like, a comment, and subscribe to stay up to date with all of our latest episodes. You can also follow us on Facebook, Instagram, X, and LinkedIn, and sign up for our newsletter on albertalandinstitute.ca. Thank you so much for tuning in to the Land Use Podcast.